To model a sex influence trait, I'm going to use an alien species. This would be very similar to male pattern baldness. So in my alien species, I've got an allele that results in having balls on the top of their antenna, and having balls is one allele. Now, it's difficult to use a capital or lowercase because it switches. So instead what I'm going to do is I'm going to use an A for antenna, since both of these are talking about antenna, but one of the alleles will have a B on it for balls, and the other allele will have an N on it for no balls. Since having the antenna balls is dominant, males that have antenna balls can either have 2 ball alleles, or they can have 1 ball allele, which will mask the not having balls allele. A female that has antenna balls is recessive, so having the antenna balls can only occur if they have 2 antenna ball alleles. If we look at individuals without antenna balls, in males not having antenna balls is recessive. So they're going to have an antenna allele with a knot and an antenna allele with a knot, because if there was an antenna ball allele, the balls would cover up the knots. Females, conversely, not having antenna balls is dominant, and so females can be heterozygous, or females can be homozygous for not having antenna balls. So let's look at our alien parents. If we have an alien male who is heterozygous, that means that he's going to have this genotype. And if we have a female with an antenna ball, her only possibility is this one. So we can make a Punnett square. And we can put one parent above and the other parent on the side, and then fill in the boxes. So when we look for the possible phenotypes in the offspring, we can look for a male with antenna balls. A male with antenna balls is going to need to have this combination. And so we can look for a BB or a BN, which includes all 4. So 100% of the kids fit that category, but only half of the kids are going to be male. So we take the probability of being male times it by the probability of having the desired genotypes, and that's going to get us 1 times 4 is 4, 2 times 4 is 8, or in other words, 1/2, or 50%. A male without antenna balls is going to need to have only no antenna ball alleles. None of them have homozygous no balls, or NN. And so the probability of having a male is 1 out of 2. The probability of having NN is 0. So 1/2 times 0, anything times 0, is 0%. The probability of having female with antenna balls, well, antenna balls is recessive in females, so they have to have 2 antenna ball alleles. And that happens twice in our possible offspring genotypes. So to calculate it, we take the probability of being female, 1 out of 2, times the probability of having 2 antenna ball alleles, so 2 out of 4. And that gets us 1 times 2 is 2, 2 times 4 is 8, which gets us 25%. Finally, a female without antenna balls has 2 possible genotypes. Of those genotypes, we don't have any homozygous no balls, or NN, but we do have the heterozygous option. So once again, we start with the possibility of being female, which is 1 out of 2. We multiply that by our probability of getting heterozygous, which is 2 out of 4. So 1 times 2 is 2, 2 times 4 is 8, which gives us 25%. So if we had a heterozygous male and a female with antenna balls, we would get 50% of the offspring were males with antenna, 25% of the offspring were females with antenna balls, and 25% of the offspring would be female with antenna balls. Without antenna balls. Or, in other words, all of the males and half of the females would have antenna balls, and half of the females would not. So, don't get hung up on whether you have the A's or not. You can just do A's and B's, B's and N's, and forget the superscript thing. Don't get hung up on whether the B is first or the A is first, or the N is first. It doesn't matter. All we're looking for is, are they heterozygous or homozygous? If you have questions, make sure you contact me.